We want to find out the orbital velocity of an object. Say, for instance, it's a satellite orbiting around a planet, or it could be a planet orbiting around a star. So we have got A, B. So in this case, A is the planet, B is the satellite. So we want to find out the orbital velocity of satellite B. So this satellite is in circular motion around the planet. So there's a centripetal force acting towards the center, Fc, and from the Newton's universal gravitational law, we know that the force between this planet and satellite, you can give it by G m m over r squared. So here m is the mass of the planet and small m is the mass of the satellite. So the velocity, the linear velocity, is perpendicular to this radius here. So this is perpendicular. So Fc, the centripetal force, can be given by m v square over r. So v square r is the acceleration. So when we equate these forces, we get m v square over r is equal to g m over r squared. So we have the value v squared here, and then g m, they are all, we know the values, they are constant, m and m in this scenario, and we know the radius. So if we separate all these variables here, v squared is equal to g m over r squared multiplied by r over m. So if we cancel out m and r and r squared, we get the value g m over r. So from this, we know v is equal to g m over r. That's the square root of that. So that's the velocity. That's the orbital velocity of the satellite or the planet around the star, and this formula can be used to calculate the velocity. Say, for instance, if we are given the mass of the planet and the radius at which that the satellite is orbiting around, we can find out the velocity. So let's write this down again here. So v is equal to square root of g m over r. I would say it's good to memorize this formula, and also it's important for you to be able to derive this formula from those two equations, which are that one, equation 1 and equation 2. So the first one is the Newton's universal gravitational law, and the second one is the standard circular motion, where the force is equal to mass times acceleration. So regarding this velocity, from this we find out that if the mass of the planet is big, the velocity is big. If it's small, the velocity is small. And if the radius of the orbit becomes bigger, and velocity becomes smaller. So say, for instance, you have got a planet here, and this is one orbit, and this is another orbit. So this is A, this is B. So what can you say from here? Because they are both orbiting around a planet called X. So A and B are two satellites. So VA should be greater than VB. Do you know why? Because VA, where the radius is less than the radius at B, so VA is greater than VB because RB is greater than RA because the mass is constant. And if we compare that to, say for instance, there's another one here, the limited space, but we'll try that. And this mass is, say for instance, this is Y. And if mass my, so my is greater than mx, so can you guess what will happen to the velocity? Because the mass of planet Y is greater than mass of planet X. So what will happen? Because if we look at that equation here, the mass is kind of proportional to velocity. Like if the mass increases, the velocity will increase. So obviously the Vy should be greater than Vx because mass y is greater than mass x, so Vy should be greater than Vx. And let's look at another place where we see the velocity is, so the velocity is square root of gmor. So what we have here is that there's a star and planet O. This is a this is say for instance the sun, and this is planet A, planet B, and the planets go into elliptical orbit around the sun. So if you look at the position A and position B, um, at A the planet is close to the sun and B is not that closer to the sun. So looking at the equation that we have for the velocity gmor, we know that if the distance is bigger, then the velocity is smaller. So we can, from this one, we can conclude that VB should be less than VA. Do you know why? If we just draw a line from here to here, this is RA, RB, because RB is greater than RA. So we looked at three scenarios. One is that where if the radius is bigger, then the velocity is smaller, and if the mass is bigger, then the velocity is bigger. So the mass, when we talk about the mass is about the mass of the object. The other one is orbiting around. So it's not the um, mass of the satellite or the planet here. So, and the third thing we need to understand that the velocity doesn't depend on the mass of the satellite. Say for instance, if the satellite has a mass of m or small m, the velocity doesn't depend on the mass. It depends only on the mass of the star here. So, so if we look at this one, so velocity depends only in this big M. It doesn't depend on the small m. So this is a question on finding out the orbital speed from the given data. So it's orbiting Earth, and the mass of Earth is given here, and we're given the radius of Earth, and we know the universal gravitational constant. So in exams, sometime you may have to find g from the data sheet and the radius of Earth from the data sheet and even the mass of Earth. So what we're going to do is we're going to use the formula that we studied before. So the velocity, which is the orbital velocity, is equal to g m over r. So we got everything. But one thing we need to be very careful, the radius is actually from the center to this point. So what we have is the radius of Earth, which is this one, and we are given the altitude. So R in our case is going to be the radius of Earth, which is 6.38 times 10 to the power 6 plus 400 kilometer, that is 400 times 10 to the power 3 meters. So what we're going to do now is we're going to substitute all those values and find the velocity. So the velocity is going to be equal to g is 6.67 times 10 to the power minus 11 Newton meter squared kilogram minus times the mass of the Earth, mass of Earth, so which is 5.97 times 10 to the power 27 kilogram and divided by R. So R is what we need to be very careful. We already got it here, which is 6.38 times 10 to the power 6 plus 400 times 10 to the power 3. And we need to get the square root of that. So if you put that in your calculator, and so this is a meter, this is meter, and you will get the result as 27,600 kilometer per hour.